Okay. Born-Haber cycle is the next section, and it's something you can put in with other areas, but I kind of leave it here because we talk a lot about bonds and states of matter, and I think it fits here as well. This is where I've always kind of taught it. So anyway, Born-Haber cycle is a process. It's a way of um, figuring up how much energy you get when you're creating an and this is really really important when you're creating 1 mole of an ionic solid. So we're going to be finding an energy value. So we're going to be finding, and you guys have done this before, we're going to be finding a delta H. But this delta H is very specific. It's based upon making 1 mole of an ionic solid. So like calcium chloride. What is delta H if I make calcium chloride? And that is called lattice energy. So that would be delta H lattice. Okay, now it's very specific in the fact that we're making the calcium chloride from the gas ions. So it'd be like calcium as a gas plus chlorine as a gas, then makes the calcium chloride as a solid. So it's super duper specific. And so the lattice energy is always a gas with a charge plus a gas with a charge makes a solid. All right. So a gas plus a gas is going to give you a solid. That's lattice energy. Okay. Now, the Born-Haber cycle is a mathematical way to calculate this. So this is math. So we can do this with math. But you can also do some predicting. So I'm going to show you the predicting first. And so this here is predicting energy of a compound if you're not going to go through and do all the math with all the individual parts. And so this is predicting if you're just given like 3 chemicals or 4 chemicals and you're going to compare them. So there's 2 ways to do this. So this lattice energy, remember enthalpy and energy are the same thing, can change in 2 ways. It can change based upon size, and it can change based upon charge. So size. So we have to remember a little bit about how the periodic table works in terms of size. So in terms of size of atoms and size of ions, the way size works is that as you go down the periodic table, things get bigger. And as you go across the periodic table, things get smaller. This is the size trend. So what we can predict about lattice energy is that as things get bigger, see, we got things getting bigger, lattice energy goes down. So you have less lattice energy if things are bigger. And if you look at the negative, the anions, same trick. As they get bigger, the energy goes down. So we should probably write a definition to remember. So we're going to write as ions get larger, and we're talking about their size. Forgot my E. Then lattice energy decreases. So they go in opposite directions. Okay, so as ions get larger, then their lattice energy gets smaller. So this is an opposite or an inverse relationship. Charge is a direct relationship. So look at the charge. So if you look at this, you have NaCl, and that would be a +1 and a -1 versus Mg, run out of space here, versus MgCl2, which would be a +2 and a -1. So this is opposite. Look at the pattern. 771 versus 2,493. And I'll zoom in on this. So look, as the charge gets bigger, so does the lattice energy. And you can look at the minuses the same way. You had -1 and -2, same trick. All right, so we need to write that down. And I kind of ran out of space, so I'm going to have to put it like right here. So I'm going to write down for charge, going to write as charge increases, so does lattice energy. Now, you only are going to do this if you're predicting between a couple of chemicals, right? So this does come up. It's not super common, but if I gave you 4 or 5 chemicals, you should be able to use this to predict, oh, without doing any math, this should have a bigger lattice energy, or this should have a smaller lattice energy. So it's direct versus an inverse relationship. Okay, here's a problem, and we're going to have to go through and work this problem, but I got to check our time here on this video to do this whole example. And so I'm going to show you how to do example 11 and 12. And they're kind of complicated, but let's remember they're just Hess's law. They're similar, where you have a target equation and you're manipulating things to get to a target equation. And so the